Now, let's just look at a carbon backbone. So that's, and I'm just going to ignore the hydrogens here, just to make it easy to see. Here's my carbon backbone, and this, as written, is, of course, polyethylene. But let's say I started with, instead of polyethylene, I started with a substituted polyethylene, and then carried out my addition reaction. Well, that means every other carbon better have this R group on it. So let's say this is my every other carbon. Starting here, I got to put an R group. Now remember, I have a choice. I can put it on the hydrogen, the carbon bond going into the board, or I can put it on the carbon bond coming out of the board. And what did I do here? I guess I put it on the one coming out of the board. And then, of course, there's a hydrogen going into the board behind it. So every other carbon, I go here, now I have a choice where I can put it, right? This is the stereochemistry part. I can either put it behind or in front. If I put them, every other one in front, we call this isotactic. Isotactic. Let me get it correct. Now you can read it. Isotactic, because each mer shares the same stereochemistry. If I did the situation where I exchanged, whoops. So let's say I put this one in front, and then I'll make this red, this one in back, this one in front, this one in back, this one in front. You can see that the stereochemistry reverses each time, and that's called syndiotactic. And then there's finally probably the most important one is atactic, which is just random. Now this, as in your reading, tells you that you can do these tricks in the presence of very special catalysts. These catalysts actually play the role of placing, in the growing polymer, placing the side group in exactly the same position each time. Now this is, so here's just a picture. Let me go back here. That's a picture of this, and this is polyvinyl chloride, obviously, big chlorine atom. And in the atactic case, it's just random. The chlorine sometimes is in front, sometimes it's in back. In the isotactic, you can see it's always in the back. And in the syndiotactic, exchanges. This one's in front, that one's in back, this one's in front, that one's in back, so forth. So that's polyvinyl chloride. Now, why does one care? Well, it affects the properties. So let's look at atactic polystyrene. Atactic polystyrene. So remember, polystyrene, we had it up here someplace. Yeah, that one up there, polystyrene. This one, because it's atactic, when it tries to form a crystal, there's no regular array to make a nice crystal. And so you always get amorphous. It's always amorphous. It has a TG of around 90 degrees C. Right? So it's a glass. We are room temperature polystyrene is a glass. Now, you can make syndiotactic. It has a melting point because it crystallizes. Syndiotactic means there's a regular array now. So when it folds back on itself, it can find a nice, perfect arrangement. It gets a melting point around 270 degrees. But it's not fully crystalline. So what do you think the TG is? So do you think the glass formed from atactic polystyrene is much different than the glass formed from syndiotactic? No. And in fact, it isn't. TG is around 100 degrees C, as best they can measure it. Now, turns out it's difficult to make syndiotactic polystyrene. It's rather slow, so it's made, but it's a rather expensive polymer. On the other hand, I scrounged around for some polystyrene things. Oh, here it is. So jewel cases. What do you hate about jewel cases? They break, right? So it's a glass. Polystyrene is amorphous. You're below the TG, and it does that. I just hate it.